Using only two legs of a three-phase service creates an unbalanced load, which can put stress on the electrical system and lead to equipment failures. The voltage on the two used legs will be lower than the full three-phase voltage, which can affect the performance of appliances and equipment. The National Electrical Code, or NEC, requires that commercial buildings with a three-phase service use all three phases for power distribution. An unbalanced load can cause electrical fires due to overheating. Utilities often charge higher demand charges for unbalanced loads, resulting in increased electricity costs. An unbalanced load reduces the power factor, which can also lead to higher electricity costs. 4 air conditioning units and an elevator are significant electrical loads that may not operate at full capacity on a two-phase system. Using only two phases limits the electrical capacity for future expansion or upgrades. Equipment manufacturers may void warranties if their products are not used on a balanced three-phase system. It is strongly recommended that the general contractor use all three phases of the service for the following reasons. Firstly, it reduces the risk of electrical fires and equipment failures. Secondly, it meets NEC requirements. Thirdly, it optimizes the electrical system and minimizes electricity costs. And fourthly, it allows for expansion and upgrades without compromising electrical capacity. Now let's delve into each of these aspects in more detail. When a three-phase electrical system is intentionally or unintentionally operated with an unbalanced load, it introduces several problems that affect efficiency, safety, and equipment lifespan. An unbalanced load means that the current drawn from each of the three phases is not equal. This inequality can lead to overheating of conductors, transformers, and other electrical components because the phases with higher current experience increased resistive losses. This is governed by Joule's law, which states that the heat generated is proportional to the square of the current, I squared R, where I is the current and R is the resistance. Consequently, the components can degrade faster, leading to premature failure and potential fire hazards. Transformers are particularly vulnerable. They are designed to operate with balanced currents in each of their windings. An unbalanced load causes unequal heating within the transformer core and windings. This unequal heating reduces the transformer's efficiency and shortens its lifespan. Furthermore, unbalanced currents create circulating currents within the transformer, exacerbating heating and losses. The voltage on the two phases being used will be lower than the full three-phase voltage. Three-phase systems are designed to provide a consistent and balanced voltage across all three phases. When only two phases are utilized, the voltage stability is compromised. This can affect the performance of connected appliances and equipment, potentially leading to reduced efficiency, malfunction, or even damage. Motors, for example, rely on balanced voltage to operate correctly. Unbalanced voltage can cause motors to overheat, vibrate excessively, and consume more energy. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for safe electrical installations in the United States. It mandates that commercial buildings with a three-phase service use all three phases for power distribution. This requirement is in place to ensure balanced loading, efficient operation, and overall safety of the electrical system. Failure to comply with the NEC can result in significant penalties, including fines, project delays, and legal liabilities. Compliance with the NEC is not merely a suggestion but a legal and ethical obligation for electrical contractors and building owners. Ignoring this code can lead to hazardous conditions and severe consequences. An unbalanced load can cause electrical fires due to overheating. As previously mentioned, unbalanced loads lead to unequal current distribution, causing some conductors and components to overheat. This overheating can degrade insulation, create hot spots, and eventually lead to electrical fires. The risk is especially high in older installations where the insulation may already be compromised. Regular inspections and maintenance are essential to identify and mitigate potential fire hazards associated with unbalanced loads. Utilities often charge higher demand charges for unbalanced loads, resulting in increased electricity costs. Utility companies typically impose demand charges based on the peak power consumption during a billing cycle. Unbalanced loads can increase these demand charges because the system operates less efficiently, requiring more power to deliver the same amount of useful energy. This inefficiency translates to higher electricity bills for the consumer. Furthermore, some utilities monitor the balance of three-phase loads and penalize customers for excessive imbalance. These penalties are designed to encourage customers to maintain balanced loads, thereby improving the overall efficiency and stability of the power grid. An unbalanced load reduces the power factor, which can also lead to higher electricity costs. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a larger portion of the current is reactive, meaning it does not contribute to useful work. Utility companies often charge additional fees for low power factors because it increases the burden on the power grid. An unbalanced load exacerbates the problem of low power factor by introducing additional reactive currents. Correcting the power factor through the use of capacitors or other power factor correction equipment can significantly reduce electricity costs. 4 air conditioning units and an elevator are significant electrical loads that may not operate at full capacity on a two-phase system. Air conditioning units and elevators are high-power devices that require a stable and balanced power supply to operate efficiently and reliably. Operating these devices on a two-phase system instead of a balanced three-phase system can lead to reduced performance, increased energy consumption, and potential equipment damage. Air conditioning units may struggle to maintain the desired temperature, while elevators may experience jerky movements or reduced lifting capacity. It is essential to ensure that these critical loads are properly powered to maintain their performance and prolong their lifespan. Using only two phases limits the electrical capacity for future expansion or upgrades. When a building is initially wired using only two phases of a three-phase service, it severely restricts the capacity for future electrical expansion. As the building's needs grow, adding new equipment or increasing the load becomes challenging and costly. Upgrading the electrical system to utilize all three phases may require extensive rewiring and equipment replacement. Therefore, it is prudent to plan for future electrical needs and install a fully functional three-phase system from the outset. Equipment manufacturers may avoid warranties if their products are not used on a balanced three-phase system. Many electrical devices, particularly motors, transformers, and power supplies, are designed and warranted for operation on a balanced three-phase system. If these devices are operated on an unbalanced system, it can cause undue stress, overheating, and premature failure. Manufacturers often include clauses in their warranties that void coverage if the equipment is used outside of its specified operating conditions, including balanced voltage and current. Therefore, it is crucial to ensure that all electrical equipment is connected to a properly balanced three-phase system to maintain warranty coverage and avoid unexpected repair costs. It is strongly recommended that the general contractor use all three phases of the service for the following reasons. Firstly, it reduces the risk of electrical fires and equipment failures. A balanced three-phase system ensures that the current is evenly distributed across all conductors and components, minimizing the risk of overheating and electrical fires. Secondly, it meets NEC requirements. The National Electrical Code mandates the use of all three phases in commercial buildings with a three-phase service, ensuring compliance with safety standards. Thirdly, it optimizes the electrical system and minimizes electricity costs. A balanced system operates more efficiently, reducing demand charges and improving power factor, which translates to lower electricity bills. Fourthly, it allows for expansion and upgrades without compromising electrical capacity. A fully utilized three-phase system provides ample capacity for future electrical needs, avoiding costly upgrades and rewiring. In summary, opting to use only two phases of a three-phase electrical service in a commercial building is fraught with risks and inefficiencies. It introduces unbalanced loads, compromises voltage stability, violates NEC standards, increases the risk of electrical fires, inflates electricity costs, limits equipment capacity, hinders future expansion, and potentially voids equipment warranties. The prudent and responsible approach is to fully utilize all three phases of the service, ensuring a safe, efficient, and reliable electrical system that meets current and future needs. By adhering to best practices and complying with the NEC, building owners and contractors can avoid costly problems and maintain a high standard of electrical safety. Now let's consider the specific implications of using only two phases in a commercial building such as a church with classrooms. The electrical demands in such a building can vary significantly based on the activities conducted. Lighting, heating, ventilation, air conditioning, and the use of electronic equipment all contribute to the overall load. An unbalanced system can disproportionately affect these different loads, leading to performance issues and increased costs. For example, lighting systems may experience uneven brightness, HVAC systems may struggle to maintain consistent temperatures, and electronic equipment may be more susceptible to malfunctions or failures. Moreover, in a church setting, the electrical system must be reliable to support essential functions such as sound systems, projection equipment, and other audio-visual tools used during services and events. An unstable or inefficient electrical system can disrupt these activities and detract from the overall experience. Therefore, maintaining a balanced and robust electrical infrastructure is particularly important in such environments. Now, let's address the specific NEC requirements that pertain to three-phase electrical services in commercial buildings. The NEC provides detailed guidelines on the installation, wiring, and protection of electrical systems to ensure safety and prevent hazards. Some key sections of the NEC that are relevant to this discussion include Article 220, which covers branch circuit, feeder, and service calculations, Article 215, which addresses feeders, Article 230, which pertains to services, and Article 310, which provides requirements for conductors for general wiring. These sections outline the requirements for sizing conductors, overcurrent protection, and grounding, all of which are critical for maintaining a balanced and safe three-phase system. Failure to comply with these requirements can result in code violations, fines, and potentially dangerous conditions. It is therefore essential for electrical contractors to have a thorough understanding of the NEC and to adhere to its provisions when installing or modifying electrical systems. Let's consider the financial implications of operating an unbalanced three-phase system. As previously mentioned, utility companies often impose demand charges and penalties for low power factor. These charges can add significantly to the overall electricity costs, especially in commercial buildings with high power consumption. Demand charges are typically based on the peak power demand during a billing cycle, while power factor penalties are assessed when the power factor falls below a certain threshold, such as 0. In line, an unbalanced load can exacerbate both of these issues, leading to higher costs. In addition, operating equipment on an unbalanced system can reduce its efficiency and lifespan, leading to increased maintenance and replacement costs. For example, motors may consume more energy and require more frequent repairs, while transformers may overheat and fail prematurely. These costs can quickly add up, making an unbalanced system a financially unsound choice. Now, let's discuss the potential long-term consequences of using only two phases in a commercial building. Over time, the cumulative effects of an unbalanced load can lead to significant damage to the electrical system and equipment. Conductors may degrade, insulation may break down, and components may fail prematurely. These issues can result in increased downtime, higher maintenance costs, and potentially hazardous conditions. In addition, an outdated or inefficient electrical system can reduce the value of the building and make it less attractive to potential tenants or buyers. Upgrading the electrical system to a fully functional three-phase configuration can be a significant investment, but it is often a necessary one to ensure the long-term viability and safety of the building. Now, let's consider the practical steps that can be taken to address an unbalanced three-phase system. The first step is to conduct a thorough electrical audit to assess the current loading on each phase. This audit should include measuring the current, voltage, and power factor on each phase under different operating conditions. The data collected from the audit can be used to identify the sources of imbalance and to develop a plan for correcting them. The next step is to redistribute the loads to achieve a more balanced configuration. This may involve moving circuits, rewiring equipment, or adding new circuits to balance the load. In some cases, it may also be necessary to upgrade the electrical service or install additional transformers to provide sufficient capacity. In addition, power factor correction equipment, such as capacitors, can be installed to improve the power factor and reduce electricity costs. It is important to work with a qualified electrical contractor to ensure that all work is performed safely and in compliance with the NEC. Finally, it is essential to establish a regular maintenance program to monitor the balance of the three-phase system and to address any issues that may arise. This program should include periodic inspections, testing, and maintenance of all electrical components. By taking these steps, it is possible to maintain a balanced and efficient three-phase system that provides reliable power and minimizes costs. In conclusion, the decision to use only two phases of a three-phase electrical service in a commercial building is a misguided one that can lead to numerous problems. It is essential to fully utilize all three phases to ensure a safe, efficient, and reliable electrical system that meets current and future needs. By adhering to best practices, complying with the NEC, and working with qualified electrical professionals, building owners and contractors can avoid costly problems and maintain a high standard of electrical safety. And that wraps up our discussion on the critical importance of utilizing all three phases in a three-phase electrical system. Remember, a balanced system is a safe, efficient, and cost-effective system.